Howdy, welcome to Math 153 Elementary Statistics. I am Lance Curtis, and this is the lecture for sections 5.3 to 5.4. As I mentioned in the previous lecture, Chapter 5 is all about probability distributions, and in particular the binomial probability distribution. There is a fifth section in your book for Chapter 5, which treats the Poisson distribution. We're not going to look at that. If it's something that you end up needing in your career field that you go into, you can examine it there. For our purposes, we're going to stick with the binomial probability distribution, which is the subject of today's lecture. So let's dive in. The key concept for this first section on the binomial probability distribution is about the basic definition, notation, conventions of how we work with it, that sort of thing. Overall, the binomial probability distribution allows us to deal with circumstances where the outcome can be classified in one of two ways. So typically you're looking at, say, a quality control process where everything that comes off a line, for example, is either acceptable or defective. This could also be used in actuarial applications. So, people survive or they die, and you use this to develop a risk model that can then go into informing how you write an insurance contract. So, this binomial probability distribution has some really useful applications, but there are some requirements that need to be met, and all the requirements need to be met in order for a probability distribution to be binomial. The first requirement is that the procedure has a fixed number of trials. So this isn't something that goes on ad infinitum. There's no infinity here. It's a fixed number of trials. And because we're looking at a number of trials, we're talking about a whole number, not a part. Okay? So the number of trials is actually a discrete data value. The trials must be independent. Okay? We understand that independence in this context means that, the outcome, the probability of any one outcome is not determined or affected by the outcome or probability of any of the other outcomes. So the trials must be independent. In addition, each trial must have all outcomes classified one of two ways. Okay? Well, we typically, in dealing with the binomial probability distribution, refer to these two categories as success and failure. The probability of a success must remain the same in all the trials. Okay? So the trials are independent, and each trial has the same probability of success. If any one of these requirements are not met, then the probability distribution is not binomial, and you need to fit your distribution to a different type of probability distribution. However, if you can meet all four of these requirements, then your probability distribution, by definition, is binomial. Now, once we've ascertained that a distribution is binomial, we need to understand certain notation that's used in the calculation of probabilities and related characteristics to the binomial distribution. So first, we're going to use the lowercase letter n to denote the number of fixed trials. Okay, again, this is a whole number. The lowercase letter x will denote a specific number of successes in n trials. Okay, so x is also a whole number. Okay, and it can be anywhere between 0 and n inclusive. The uppercase letters s and f we will use to denote success and failure. And then the lowercase letters p and q are the probabilities of success and failure in one of n trials. Okay, now remember, the binomial distribution means that all trials the outcome can only go one of two ways, success or failure. So then it follows that the probability of success and the probability of failure have to add together to equal 1. This is a very useful property because if we know the probability of success, we can get the probability of failure. Or if we know the probability of failure, we can get the probability of success. We just take what we know and subtract it from 1. And that gives us the other probability. Now, the probability of X is what we use to denote the probability of getting exactly X successes among N trials. So we're going to take a fixed number of trials, and we're going to say what's the probability that X of those trials are actually successes. The equation that we use to calculate that probability we see here at the bottom of the screen. So this is the actual equation that's used to calculate probabilities, and when you calculate this probability out for each of the number of fixed trials in your distribution, you end up with something that looks like this. So here's a binomial distribution where n is 15. Okay, so there's 15 fixed trials. And what this is showing you is the probability of success in a certain number of those 15 trials. And it changes depending upon what number you choose. So what's the probability that all 15 of our trials will be successful? Well, as you can see here, it's pretty close to 0, pretty non-existent. But what's the probability that, say, 7 of the 15 trials are successful? Well, 7 is your X. Come up here, and we see it's about 20%. So this is a distribution showing you the probability of success that a certain part of a whole will actually result in success. Let's take a moment to consider what each of the different parts of our equation represent, because math is a language, and like all languages, the symbols and characterizations that are used to convey meaning have a physical representation. So let's look at the parts of our equation and see if we can interpret what they actually mean. This first part is the number of outcomes with exactly X successes among N trials. This should make sense because the probability of X is defined earlier as the probability of having X successes among N trials. Now, this part of the equation should actually look familiar to you. You may remember from chapter 4 where we talked about combinations. You should recognize this equation as the form of the equation used to calculate combinations. And indeed, it is identical. So what we're looking at with the binomial distribution, when we say the probability of X successes among N trials, we're taking N trials, X at a time, and the order does not matter. That is by definition requiring calculation for combination. So that's the first part of our probability equation. The second part of our equation is looking at the probability of X successes among N trials. So we're going to take the total number of outcomes and multiply it by our probability of success, because certain number of our trials are successful. Now, looking at this part of the equation, we see that P is the probability of success. Okay, so if we have, say, 5 trials and 3 of them are successful, we're going to want to take that probability of success and multiply it by itself 3 times to represent the 3 successes. Okay, but the other 2 trials are failures, and so that's where this last part of the equation comes in. To represent those trials, which were not successes but failures, we take the probability of failure and multiply it by itself for the number of trials that are actually failures. So if we have, for example, 5 trials that end up with 3 successes, then we're going to take the probability of success, multiply it by itself 3 times, and then we're going to take the probability of failure, which is 1 minus the probability of success, and we're going to multiply it by itself twice, or 5 minus 3 times. So total number of outcomes times the probability of success for each trial that is successful times the probability of failure for each trial that is a failure. Let's actually apply this equation to a real-world situation. Supposing a survey reports that there's an 85% chance that a randomly selected adult will know what Twitter is. Now that 85% number may seem high or low to you, depending upon your individual involvement with social media. But let's just say that this is what the survey reports. So, given that the survey reports an 85% chance that a randomly selected adult will know what Twitter is, what's the probability that if we take 5 randomly selected adults, 3 of them will know what Twitter is? Well, the way this question is clearly calling for a binomial probability calculation. So here, first, whenever you deal with binomial probability distribution calculations, you need to define what success is. That's the first step. Here, from the way that the question is worded, success is going to be knowing what Twitter is. Second, we want to define the variables, and there's 4 variables that we need to look at: N, X, P, and Q. Okay, so we look at our problem statement. N is the number of fixed trials. Okay, so there's 5 people we're selecting. That's the number of trials that we're going through with the probability distribution. So N is going to be equal to 5. Of those 5, we're taking 3. So X is going to be equal to 3. Our probability of success is knowing what Twitter is. So the probability of knowing what Twitter is 85%. So that's going to be P. Q we can then derive by just taking P and subtracting it from 1. So 1 minus 85% gives us 15%. So now that we have these 4 variables defined, we're ready to perform our calculation. Okay, here's our equation for calculating probability of X successes among N trials. So we just plug into our equation what we know, and then calculate this out, and out comes 13.8%. That's really all there is to it. Now, for most of your homework problems, you're going to actually be using StatCrunch, which will calculate these probabilities, has a calculator to calculate these probabilities for you. Okay, but it is nice to know how to calculate this by hand so you can see where the numbers are coming from and how they combine together to get the actual end result. This brings us to the last section in Chapter 5 we'll examine, which is the parameters for the binomial distribution. So let's dig into this. When we're talking about parameters, what we're really talking about is the mean, the variance, and the standard deviation. But we want to do more than just calculate these characteristics. We want to be able to interpret them and understand what it is that they mean. So first, let's recall some basic conventions that we use when calculating with respect to the binomial probability distribution. So N is the number of fixed trials, is by definition a whole number. P is going to be the probability of success in one of those N trials, and then Q will be the probability of failure in one of those N trials, where P and Q add together to equal 1. Okay, so with this under our belts, let's look at calculating the mean. To calculate the mean for a binomial probability distribution, we're going to take the number of fixed trials and multiply by the probability of success in one of those trials. This is the mean value of a binomial probability distribution. Calculate the variance by taking the number of fixed trials and multiplying it by the probability of success in one of those trials, and then multiplying by the probability of failure in one of those trials. You may notice N times P is the same thing as the mean. So we can calculate the variance if we know the mean value and the probability of failure in one of those N trials. Once we know how to calculate variance, it becomes really easy to calculate standard deviation. All we do is just take the square root. And of course, since N times P is the mean, we can calculate standard deviation if we know the mean. So we don't even need to know the variance to calculate standard deviation. If we know the mean value of the binomial probability distribution and the probability of failure, those two values alone can give us the standard deviation. Let's apply these characteristics to a real-world instance. So, brand recognition is something that all companies are interested in if they want their businesses to be successful. The McDonald's brand has a 95% recognition rate. So there's a special focus group forming. We're going to take 12 randomly selected adults for the focus group. Okay, and as part of our statistical characterization for this focus group, we want to find the mean and the standard deviation. Well, the mean, we just learned how to calculate the mean for binomial probability distribution. That's just taking the number of trials and multiplying it by the probability of success. Here the number of trials is 12 because we're taking 12 randomly selected adults. The probability that any one of them will recognize the brand is 95%. So multiply those two values together and we get 11.4 for our mean value. Standard deviation then becomes really easy to calculate. Here's our equation for calculating standard deviation. So we can take the number of trials times the probability of success times the probability of failure. Remember, probability of success and failure have to add together to be 1. So if the probability of success is 95%, the probability of failure will be 5%, which is 1 minus 95%. Punch all this out in your calculator and you get 0.8. Notice that if you take 11.4, multiply it by 0.05, and then take the square root, you'll also get the same number, 0.8. So with these characteristics for our distribution, we're now prepared to answer another question. Suppose we want to know the range for the usual number of people who recognize the McDonald's brand. So of these 12 randomly selected adults, what's the range of usual values that we can expect for brand recognition? Well, previously we would just use the range rule of thumb, and we can do that here with binomial probability distributions. We know what the mean and standard deviation are, so let's just use the range rule of thumb to calculate our usual value range. The minimum value for the range is going to be 2 standard deviations less than the mean value. So we plug in those values, out comes 9.8. The maximum value for our range is just going to be 2 standard deviations above the mean. So again, plug in those numbers, punch out the answer, we get 13. So somewhere between 9.8 and 13 would be our usual range of values. Okay? Note that it's not unusual to have all 12 of those randomly selected adults inside our range of usual values. And we would expect it to be there because it's a 95% recognition rate that we're dealing with. So we would expect 12, which is the total number of adults we're selecting, to be in that range of usual values. However, if we choose, say, a lower number, say like we wouldn't expect only 9 of 12 randomly selected adults to recognize McDonald's because the recognition rate is almost 100%. So 9 falls out of the usual value range, is therefore an unusual value. That's all we have for this lecture today, because that's pretty much all there is with the binomial probability distribution. So if you have any questions, you know where to get a hold of me. Otherwise, I will see you in class. Thanks for watching.